On TMUA and also ESAT Maths 2, students will very frequently be required to consider the range of a function, either outright determining the range, or perhaps just the minimum or the maximum. Given that the required differentiation knowledge is extremely basic, you're not even expected for these exams to know the product and chain rules. It can be quite difficult to see how to proceed. After all, the standard approach to the minimization and maximization of functions is to look for turning points. An idea that recurs again and again is that complicated-looking functions will actually be compositions of much simpler functions. There is a very simple result relating to the range of compositions of functions which renders such problems almost completely trivial. And we're going to explore this idea in this video. So the key result that we need is very simple. Suppose we have some complicated looking function, but we manage to identify that it's actually the composition of two simpler functions, f of g of x, where f and g will certainly individually be simpler than f of g. The idea is that the range of this function, f of g of x, is the same as the range of f of x on the restricted domain equal to the range of g. So the idea is I don't need to consider f of g as a complicated function in its own right using, say, the chain rule with differentiation for the purpose of finding the range. I can get everything I need by thinking about f and g individually. Now this result is actually very simple and very obvious if you think about it. The significance of the fact it's a g inside f rather than just x is that f is only able to take as its inputs the things that can be spat out by g. So I'm just looking at what are the things that f can output when as its input it takes something that was an output of g. So the motto is, from a range of functions perspective, a composition of functions is really equal to just a domain restriction. So we don't need to do anything complicated, with beyond syllabus differentiation, say, to study these sorts of functions. So let's work through a few examples. So let's begin by thinking about the function cos of sine of cos of x. So obviously this is a composition of three functions. Cos goes into sine, and then that function goes into cos, but we can simply iterate the logic to build the range from the inside out. So the range of cos we should certainly know. So the range of cos is just -1 to 1, where I don't yet have a domain restriction because that's the innermost function. That's like the g in my language. So because sine of cos is f of g in the language we used earlier, I know that when I'm considering the range of sine of cos, I'm actually going to consider the range of sine on the restricted domain -1 to 1. Now, we're working in radians here, by the way. So although you might argue along the lines of, well, sine is an increasing function on the interval, say, -π/2 to π/2, this is entirely within the increasing portion. So I obviously get the smallest output with the smallest input and the biggest output with the biggest input. Now, that's true because it's an increasing function. But remember that in general, when you have a domain restriction, you can't just assume smallest in equals smallest out. That's only true for an increasing function. It's good practice to use a graph just to see what's going on. So, we should know the graph of the sine function like the back of our hands. So let's just draw a quick graph and observe the obvious. So sine, I'll draw it up to the first peak and from the first trough, because the first peak is at π/2 and I know that 1 is smaller. And likewise, the first trough is at -π/2, so -1 is smaller. So obviously, by definition, I output sine of 1 at 1, and I output sine of -1 at -1. But because sine is an odd function, that's the same as minus sine 1. So when I look at what can be achieved on my good domain, when I look at what can be achieved from -1 to 1, Well, I can achieve everything between the values minus sine 1 and sine 1 as outputs. Because on this vertical line, I'm able to achieve all of those vertical values. So I can see that the range of sine of cos of x is simply minus sine of 1 to sine of 1. Now we just have one layer to go. So if we now consider cos of sine of cos of x, we're just going to consider the range of cos, but the domain restriction now is minus sine 1 to sine 1. Because I'm feeding this thing to cos, and that's the range of the thing that cos is eating. So that's the range of things that can actually be fed to cos as an input. Now, cos is not an increasing function on minus sine 1 to sine 1. It goes up, then down. So let's draw a graph. So cos between, say, minus pi by 2 and pi by 2 is going to do this. So it's got x-intercepts at minus pi by 2 and pi by 2. And so I'm looking at sine 1, which is obviously smaller than 1 and therefore also smaller than pi by 2, and minus sine 1. So I'm looking at what are the outputs I can get, what are the y coordinates between those values. Well, I get the smallest output by going to the far end of the domain, and that's obviously cos of sine of 1. So cos of sine of 1 is the same as cos of minus sine of 1 because cos is an even function. So this is the lowest I can get at the end of the domain, and I can get the biggest output by going right to the middle of the domain and actually putting x equals 0 in. So you can see that the smallest you can get is that cos of sine of 1, and I get my biggest output in my allowed domain actually here. That's when x is 0, or, the thing going into cos is 0, and that output's 1. So here's our final range. We haven't had to do anything fancy with calculus. We've just built it up gradually from the inside out using this simple result. Let's take another example. So let's consider the function 4 sine 2x plus 3 minus cos squared 2x plus 3 plus 2 all squared. Well, first of all, given that our plan is to think of this as a composition of functions, it makes sense to start by using the Pythagorean identity, sine squared plus cos squared is 1, to write this as a function of sines only, because then I can think of it as being sine 2x plus 3 put into some other function. So I'll start by writing that this is the same thing as 4 sine 2x plus 3 minus, so that's going to be 1 minus sine squared, so minus minus makes plus, sine squared 2x plus 3, and then 2 minus 1 makes 1. So now, as my first layer, I'm also going to have to square it, but I can consider 4x plus x squared plus 1 on the domain minus 1 to 1. Because, it doesn't matter that it's a 2x plus 3 going into the sign. As x varies across all values, so does 2x plus 3. So the fact it's that going into sine isn't really a domain restriction. Clearly, as x varies, I can achieve all the outputs of sine, which is everything from minus 1 to 1. And at least at first, I'm plugging sine 2x plus 3 into the quadratic 4x plus x squared plus 1. So really, that means I'm looking at the restricted domain minus 1 to 1. So I'll first of all figure out the range of that. That gives me the range of this bit, and then I'll think about what happens when I square it. So again, we're building these compositions up from the inside out. Now, to find the range of a quadratic, probably easiest to just complete the square, because I'll be smallest when I'm closest to the vertex and biggest when I'm furthest. So I can complete the square, x plus 2 squared minus 3. So that means we have a vertex at minus 2 minus 3. Now, minus 2 is not in my domain, but thinking about the shape of a positive quadratic, I'm obviously getting bigger as I go further and further from that vertex. So my smallest value is going to be at minus 1, because on the range minus 1 to 1, the closest I can get to the vertex at minus 2, to x equals minus 2, is going to be at minus 1. So the minimum is going to be at x equals minus 1. And at x equals minus 1, I can see from this form, I clearly output, 1 squared minus 3, which is minus 2. And the furthest I can get from the vertex is going to be all the way at the other end of the interval, x equals 1. So at x equals 1, well, I get 3 squared minus 3, which is 9 minus 3, which is 6. So the range of this is minus 2 to 6. Now, to complete the function, I'm feeding this thing to x squared, essentially, because I'm squaring that big thing. So now, finally, I have a very easy task of considering x squared on the domain minus 2 to 6. So I'm going to get the smallest output from x squared by squaring the number smallest in size. And the number smallest in size in this domain is, of course, 0. So I can output something as small as 0. And I'm going to get the biggest output by squaring the biggest thing on the range, which is, of course, 6. So my final range of the overall function is 0 to 36. So these are really standard problems that will come up a lot on admissions tests like the TMUA and the ESAT, particularly Maths 2. We're not doing anything profound. There's no deep mathematical insight here. But if you don't have the correct framework from which to attack these problems from the get-go, it's very difficult to get an answer in the allocated time. So let's consider one final example. And this example is a bit different because rather than being given the formulae for the functions we're dealing with, we're actually just given their graphs. Now we can apply exactly the same logic. So we're given the graphs of an f, a g, and an h. We want to find the range of f of g of h. So we can just work through layer by layer. So let's begin by thinking about the range of h. Well, if I look at my graph, clearly the range of h is just all values from minus 4 to 4, because I achieve a maximum of 4, a minimum of minus 4, and even just on this domain, I cross every value in between, including 0. Outside of minus 4 to 4, I'm just re-achieving values I've already hit. So I clearly hit just everything between minus 4 and 4. So now, when I'm considering the range of g of h, I'm just looking at g on the restricted domain minus 4 to 4. So here's g. What do I achieve between minus 4 and 4? Well, by minus 4, I'm up at 4. By 4, I'm up at 4. And in between, I achieve everything down to 0. So the range of g on the domain minus 4 to 4 is clearly 0 to 4. Now, g can achieve bigger values. If I put something out here into g, I'll get something bigger than 4. But because of my domain restriction, from the fact it's h that's being fed to g, this cannot arise. So now, finally, I'm considering f of x on the restricted domain 0 to 4. And if I look at f, and I ask, what do I achieve between x equals 0 and x equals 4? Well, at 0, I'm down at minus 2, and I just rise up to 0 by the time of x equals 4. So I clearly achieve all values between 2 and 0. So nothing challenging, but again, if we don't have ahead of time the framework that we're going to consider restrictions of domain as a result of composition, this question looks at first glance very intimidating. This is one of many techniques which form what I call the shadow syllabus of exams like the ESAT and the TMUA. Ideas which are not explicitly covered in school, and which are not formally set out on the specification for the exams, but which will nonetheless recur again and again as a way of testing your problem-solving skills and flexibility applying ideas in unfamiliar ways. If you'd like to meet more ideas from the shadow syllabus, do take a look at our other ESAT and TMUA videos, and comment below if there's anything you'd particularly like to see next. If you're interested in more intensive support with your admissions test preparation, do also feel free to visit our website, where you can learn about our preparation programs for these exams. Thanks very much for watching, and remember to subscribe.